ever imagine looking back in time, like billions of years, to see how the universe has grown and changed? Well, that's what we're diving into today. Some fascinating new research about how our universe evolved and how it might continue to change.
Right.
We're going to be unpacking an article about the Dark Energy Spectroscopic Instrument, DSI, and some pretty groundbreaking findings.
Interesting.
Get this, DESI can capture light from 5,000 galaxies at the same time.
What's fascinating here is that DSI isn't just a single telescope. It's actually a massive collaboration of over 900 researchers, representing more than 70 institutions around the world. It really highlights a global effort to understand the universe we live in.
Okay, so it's a big deal. But help me understand what it actually is. It's mounted on the Mayall telescope, right? But what makes it so special?
So DSI is essentially a giant 3D map maker of the universe. It uses something called spectroscopy to split the light from distant galaxies into its component colors, like a rainbow. This allows us to figure out how far away those galaxies are and how fast they're moving.
So, like a cosmic GPS.
That's a good way to put it. But what's truly remarkable is that DSI is mapping the universe's growth over an incredible 11 billion years.
11 billion years?
Yeah.
That's almost the entire age of the universe. So it's not just about where things are now, it's about watching how they got there.
Exactly. And the data DSI is collecting isn't just confirming what we thought we knew. It's actually pushing us to rethink our models of the universe. Remember Einstein's theory of general relativity? Well, DSI is confirming that it holds true even on this incredibly vast scale.
Hold on. You're saying gravity behaves the way Einstein predicted, even across billions of light years and billions of years? That's mind-boggling.
It really is.
Yeah.
And you know what's even cooler? DSI is showing us how even tiny differences in the distribution of matter in the early universe led to the formation of these massive structures, galaxy clusters and cosmic filaments that we see today.
It's almost like those tiny variations acted as seeds and gravity did the rest, pulling in more and more matter over billions of years to create the structures we observe today.
Yes. You could say the DSI is giving us this incredible look into the universe's evolutionary process, revealing how gravity sculpted the cosmos over time. It's like watching a cosmic time-lapse, seeing those seeds grow into these vast interconnected structures.
So DS is mounted on this powerful telescope. It's funded by the Department of Energy, which tells you how seriously they're taking this research.
Right.
And it's located on Kitt Peak, which I know is a very special place.
That's right. Kitt Peak is a site of immense cultural significance for the Tomo Odom Nation. And it's a beautiful reminder of how science and culture can intersect, each enriching the other.
I love that. Okay, so we've got this amazing instrument that's mapping the universe, confirming Einstein's theories, and showing us how these massive cosmic structures came to be. But there's more to the story, right? The article also mentioned dark energy.
Indeed. And this is where things get really interesting. Most people think of gravity as the dominant force in the universe. But DSI's data is telling a different story. Dark energy is this mysterious force that's actually causing the expansion of the universe to accelerate.
So not only is the universe expanding, but it's expanding faster and faster over time.
Exactly. Imagine a balloon inflating. But instead of inflating at a steady rate, it starts inflating faster and faster. That's essentially what's happening with the universe. And we think dark energy is the culprit.
But here's the thing. We still don't know what dark energy actually is.
That's one of the biggest mysteries in cosmology today. We know it's there. We can measure its effects. But its true nature remains elusive.
So where does DSI fit into this puzzle?
DI is providing us with more clues about this elusive force. Previous data hinted that dark energy might not be a constant force, that it might be changing over time, and DI's findings are adding fuel to that fire.
Hold on. Are you saying that dark energy might not be a constant force after all? What are the implications if it's changing?
The implications are huge. If dark energy is changing, it means our understanding of the universe's evolution and ultimate fate could be drastically different from what we thought.
Okay, I'm officially intrigued. So DSI is helping us unravel this mystery of dark energy.
Precisely. It's providing us with the most detailed measurements yet of the universe's expansion history,
Right.
which is crucial for understanding how dark energy behaves. And we're expecting even more detailed results in 2025.
Wow. It sounds like we're on the verge of some major breakthroughs in our understanding of the universe.
Yeah.
But wait, there's one more piece of the puzzle we need to talk about: neutrinos.
Ah, yes. Those ghostly particles. They might be tiny, but they play a surprisingly important role in the cosmic drama.
They're notoriously difficult to detect, aren't they?
Neutrinos are incredibly tiny. almost massless particles that rarely interact with matter. Billions of them are passing through you right now, and you wouldn't even know it.
That's wild. But how can DSI help us study something that's so hard to detect?
Well, even though they're tiny and elusive neutrinos, still have a gravitational effect on their surroundings. DSI's data is helping us narrow down the possible mass range for neutrinos by studying how they subtly influence the distribution of galaxies.
It's amazing to think that something so small can have such a big impact on the universe. It makes you wonder what other subtle influences are out there, just waiting to be discovered.
That's the beauty of science, isn't it? There's always more to learn, more mysteries to unravel, and instruments like DSI are giving us the tools to explore those mysteries in ways we never thought possible.
This has been an incredible journey so far. We've covered so much ground, from the evolution of cosmic structures to the mysteries of dark energy and neutrinos.
It has been quite a journey.
And we're not done yet.
Not at all. There's still so much more to explore.
We'll be back after a quick break to delve even deeper into the fascinating world of DSI and its groundbreaking discoveries.
Sounds good. I'm ready for more.
Welcome back. We've been talking about how DSI is giving us these new insights into the universe's evolution.
Right.
But I have to admit, it's a bit mind-bending to wrap my head around some of this.
It's true. We're dealing with concepts that challenge our everyday understanding of space and time. But that's part of what makes cosmology so fascinating.
Absolutely. Earlier, we touched on the idea that dark energy might not be constant, that it might be evolving over time. Let's dig into that a bit more. What does that actually mean for the future of the universe?
Well, the fate of the universe largely depends on the nature of dark energy. If it continues to accelerate the universe's expansion, as we're currently observing, it could lead to a scenario called the Big Freeze.
The Big Freeze. That sounds a bit ominous. What would that look like?
In the Big Freeze scenario, the universe would continue to expand indefinitely. Becoming increasingly cold and diffuse, galaxies would become more and more isolated. Stars would eventually burn out, and the universe would slowly fade into a state of maximum entropy.
So kind of like a slow cosmic fade to black. That's a bit bleak, isn't it?
Bleak, perhaps, but also incredibly vast and awe-inspiring. Imagine a universe so spread out that even the faintest whispers of light and energy are stretched thin across unimaginable distances. It challenges our perception of time and scale.
It definitely makes you ponder the vastness of it all. Are there any other possibilities besides the Big Freeze? What if dark energy doesn't behave the way we expect?
There are other theories, yes. Some physicists have proposed a scenario called the Big Rip, where dark energy becomes so strong that it eventually overcomes all other forces, even the forces holding atoms together.
Wait, so the fabric of reality itself could be ripped apart? That sounds pretty dramatic.
It's certainly a dramatic scenario,
Yeah.
but it's important to remember that this is just one possibility. And it's not necessarily the most likely based on our current understanding.
Okay, good to know. I'm not quite ready for the universe to end in a cosmic shredding event. Are there any other scenarios we should be aware of?
Another possibility, which is kind of the opposite of the Big Bang, is the Big Crunch in this scenario. The expansion of the universe eventually slows down, reverses, and everything collapses back in on itself.
So instead of expanding forever, the universe would contract, ultimately ending in a single, incredibly dense point. That sounds pretty intense, too.
It would be an incredibly energetic and transformative event, that's for sure. But again, the likelihood of this scenario depends on various factors, including the overall density of the universe, which is something scientists are still working to determine.
Right, because we also have dark matter to factor into the equation. It's like all these big cosmic mysteries are intertwined.
Exactly. And that's what makes cosmology so exciting. Each new discovery leads to more questions, more avenues to explore. It's a constant process of refining our understanding of the universe and our place within it.
Speaking of refining our understanding, let's circle back to those ghostly neutrinos. They might be tiny, but they play a big role in the universe, right?
Absolutely. Neutrinos are everywhere. They're constantly streaming from the sun, from distant supernovae, even from the Earth itself. They're a fundamental part of the universe's fabric, and understanding their properties is crucial to our understanding of both cosmology and particle physics.
They're like tiny cosmic messengers zipping through the universe, carrying information about the events that created them. I remember reading that they're incredibly difficult to detect because they interact so weakly with matter. It's like they pass right through us without a trace.
That's right. They're often called ghost particles for that very reason. But despite their elusiveness, they carry valuable information about the processes that create them. For example, studying neutrinos from the sun helps us understand the nuclear fusion reactions happening at its core.
It's fascinating to think about all the information these tiny particles hold. And how does DSI help us decode those messages?
DSI's data allows us to study the distribution of galaxies and quasars across the universe. The subtle gravitational effects of neutrinos, even though they're incredibly small, can influence that distribution in ways that DSI can detect.
So by studying the large-scale structure of the universe, we can indirectly learn about these tiny elusive particles.
Precisely. It's a testament to the interconnectedness of the cosmos. Everything is influenced by everything else, from the smallest particles to the largest cosmic structures.
It's like we're piecing together a giant cosmic puzzle, and neutrinos are some of the most challenging pieces to fit. But with DSI's help, we're getting closer to understanding their role in the grand scheme of things.
And as we continue to unravel these mysteries, who knows what other incredible discoveries await us? The universe is full of surprises.
It certainly is. Well, we've covered a lot of ground in this part of our deep dive, from the potential fates of the universe to the elusive nature of neutrinos. But our exploration isn't over yet. We'll be right back with more fascinating insights from DSI and the mysteries it's helping us unravel. Stay tuned. We're back for the final part of our deep dive into the world of DSI and its discoveries. We've explored so much, from the evolution of cosmic structures to the mysteries of dark energy and neutrinos. It's amazing to think that one instrument can help us understand all of that.
It's true. DSI is a truly remarkable feat of engineering and scientific collaboration. And we're just beginning to scratch the surface of what it can teach us about the universe.
We've talked about DSI mapping millions of galaxies and quasars, but what's the ultimate goal? What are we hoping to achieve with all this data?
The ultimate goal is to create the most detailed 3D map of the universe ever assembled. This map won't just show us where things are located. It'll also show us how they're distributed and how that distribution has changed over billions of years.
So instead of just a snapshot of the universe today,
it'll be like a cosmic flipbook, showing us how the universe's structure has evolved over time.
That's a great way to put it. And that's incredibly valuable because it allows us to study the expansion of the universe, the formation of those large-scale structures we talked about earlier, and the mysterious forces that govern it all.
So DSI's data could help us solve some of those big mysteries.
Yeah.
Like the nature of dark energy and dark matter.
Exactly. By precisely measuring the expansion rate of the universe and the distribution of matter and energy, DSI can help us refine our cosmological models and test different theories about how the universe works.
Okay, so we might finally get some answers to those big questions. Like, which of those end-of-universe scenarios is the most likely? You know, the big freeze, the big rip, the big crunch.
It's certainly possible. The more data we have, the better we can constrain those models and make more accurate predictions about the future of the universe. It's incredible to think that we might be on the cusp of understanding something so fundamental. You know, there was a quote from one of the researchers in the article that really stuck with me. They said something like, "The idea that we can take pictures of the universe and tackle these big fundamental questions is mind-blowing."
It is a powerful statement.
Yeah.
It speaks to the incredible capabilities we've developed as a species, the power of human ingenuity to probe the deepest mysteries of the universe.
We're just these tiny beings on a tiny planet. Yet we figured out how to build instruments that can look back billions of years and unravel the secrets of the cosmos. It's both humbling and incredibly inspiring.
It truly is. And I think DSI is a perfect example of that. It's a testament to the power of collaboration, bringing together hundreds of scientists from around the world to work towards a common goal.
It's a reminder that we're all connected in this grand cosmic journey, all trying to understand our place in the universe, and who knows what incredible discoveries await us. I, for one, can't wait to see what the future holds for DSI and for our understanding of the universe as a whole. It's been an incredible journey exploring these topics with you.
Right, and I think it highlights how much we still don't know, which is both exciting and humbling.
Absolutely. Well, that's all the time we have for today, but the exploration doesn't stop here. Keep looking up, keep asking questions, and keep wondering because the universe is full of possibilities.